So, lab exercise 8, brushed DC motors. Last lab exercise, at least the year I'm recording this, so. Didn't get very pretty before this, should have done that. Okay, so lab exercise 8, brushed DC motors. Introduction. In this lab, we will use a brushed DC motor to drive a rotational mechanical system with a Myrio microcontroller, measure the motor's voltage, current, and angular velocity, and characterize the motor. So, all that, and just one credit. Okay, the electromechanical systems are shown in figure 8.1. They are, let's see. They are shown here. So let's go through this for just a moment. So these are actually part of the embedded computing lab. So embedded computing lab. And this lab is set up to, I guess, help teach embedded computing and control for mechanical engineers. And there's a version of it that's up at the University of Washington, where I did my PhD work. And I collaborate with a professor up there, Joe Garbini, who has this very similar system up there. So we have this embedded computing lab set up that is set up to do more than what we're going to do with it today, but we're going to use it in this lab exercise nonetheless. So it's pretty fun. So we've got a permanent magnet DC motor right here. We've got, this is actually something that you guys have mostly seen because I think all of you are in the mechatronics class. So we've been talking about this setup here, the motor, the shaft coupler, the bearings, and the flywheel. So this is another view of that. We've been working in class on modeling that, and we're going to use that modeling and match that up with the data in this lab exercise that we're going to measure. So it's going to be fun. The rest of this, the Myrio should be familiar to you. The terminal board actually will be disconnected in at least this year's lab exercise. Maybe in the future that will be connected. But the typical C connectors this year are going to be here. And so we'll have the usual pinouts to connect to there. All of this terminal board does when it's connected is give different connectors for those C connector channels. So there's the encoder, there are two encoder pinouts there that can be used that are sort of a standard encoder connector, and then there are these RCA connectors as well for the analog ins and outs. So that's the term board. It's going to be disconnected for this lab section. On the other side, the A connector has a proto board connected to it. So a proto board can, as we've discussed, be used to solder different elements to it, different components to it. And this is soldered up to specifically have connections to the encoder, which we'll talk about in a little bit, for measuring the shaft position in the motor. And also it has some of the analog and digital outputs from the Myrio and inputs from the Myrio. So we'll be using the outputs specifically and then the encoder inputs. So something to look forward to there. So the encoder could go through this Quanser board, but I only have two connectors for that. So I had to go through the proto board for now on that. Then we have the LCD and keypad, which are used in the embedded computing lab course. So I teach a course that's really the main purpose of this apparatus, called Embedded Computing for Mechanical Control. It's currently called Embedded Computing for electromechanical systems, but changed to mechanical control. It's a little bit more specific. So this is the LCD and the keypad are used extensively in the embedded computing graduate course, and then there's also typically an undergraduate version that's offered as well that you can take, and I encourage you to take. I teach it. So finally, the last thing we'll discuss about the apparatus is the driver. Well, second to last thing, the driver, the motor driver. So this is one way to drive a motor. We're going to talk a little bit about that today before we get started, how we're driving the motor. But this printed circuit board has some an integrated circuit on it and some auxiliary circuitry that essentially drives this motor with a power supply that you can't see. It's underneath these components. We're going to look at the side view here, the front view, and we get to see the power supply. So DC power supply, so it's a constant DC power supply, not variable. It only puts out about 20 volts, and it has some significant power behind it, so be cautious. It has a warning sticker there, but don't put your fingers in there. It's a little bit dangerous, so it's not dangerous if you don't touch it, but just don't touch it. Okay, so great. So this motor driver is going to use that power supply you saw underneath to drive the motor, and it's going to be controlled with some of the connections from the myRIO through the proto board. So that's kind of the main idea there. So way back up here, the objectives are to characterize the performance of a motor. So we're not just going to take some measurements. We're going to measure a really important quantity, the transformer ratio, or equivalently the motor constant for this motor. So the torque constant, and also equivalently the back EMF voltage constant, so KT and KV. Then we're going to apply motor driving. That's another objective, is for you guys to apply motor driving, apply pulse width modulation, PWM, apply H-bridge circuits, and we'll talk about those too, and apply quadrature encoders for measurement of the shaft position of the motor, and finally to estimate electromechanical system parameters such as the motor constant. So that's the last of the outcomes or objectives. So materials used, the sort of the usual stuff. We're going to use one of the Embedded Computing Lab apparatuses though, and notice that it should be set up so that the encoder and most of the motor driver connections are pre-connected, and the connections are going to be in figure 8-7. We'll talk about the connections in a little bit. Check when you start that they are correctly connected. So I set them up, at least this year, I set them up so that they should be all connected, but I could be wrong. I could have misconnected something, or somebody could have screwed it up in a previous section. So double check all the connections. Hopefully they're good. So all of them should be there except the C-channel connections, which are left for you guys to do. So if it's properly set up, you'll only have to make those C-channel connections. But it's possible that somebody in a previous group disconnected something that they shouldn't have. So make sure you check everything, otherwise you could be in for some headaches. So also you're going to need a multimeter just to measure the couple of resistors that you're going to be using. two 330K resistors. Doesn't matter if they're 330, but I would just choose two large resistors that are similar in resistance, so we can get a voltage divider of about 1/2, which is our goal here. And then jumper wires and a breadboard are all you'll need for this lab. So, motor driving. So let's talk about this a little bit. So DC motor requires DC electrical power provided by a circuit called the driving circuit. For industrial motors, at least, these circuits must provide significant power. And for this reason, as separate from the control circuit, power supply is often used. There's a quick and dirty way to drive a DC motor at variable speed, since its angular velocity is reliably proportional to its voltage. We can place a potentiometer, which is just a variable resistor, remember, in series with the power supply and motor. So we can essentially divide the voltage down that's supplied to the motor. However, this has disadvantages that include the power being limited and dissipated at high potentiometer resistance, which corresponds to low speed, because there's low voltage and then low speed. For most applications, we will need either a current or power amplifier or a microcontroller and an integrated circuit to produce a pulse width modulation driving signal. So the latter, so the PWM driving signal, is usually more cost effective nowadays, but the former is advantageous in certain applications. So getting an amplifier, a so-called linear amplifier, is sort of the I want to say like the old school way to do this, where you can drive a motor with a smaller analog output signal. The trouble, there are some issues with the linear amplifier approach. The main one is cost, so they tend to cost more, so the electronics are more expensive. They can be less efficient than using PWM, and those are, I guess, the main disadvantages. They're a little bit more complicated to design with too. PWM is what we're going to use in this lab exercise. In the embedded computing lab, we use both PWM and linear amplifiers. So you get a little bit of both in that course. But in this lab, we're just going to use PWM, which has a distinct advantage of being cheap and easy. The main disadvantage tends to be that you can create a lot of noise with it because it's a switching supply, as we'll talk about. And the switching supply can come with some headaches, especially if there is any danger of electronic interference nearby. The linear amplifier doesn't do this, so you might want to use a linear amplifier in those cases. And linear amplifiers are kind of like they're really nice, so there's an advantage there. Oh, there is another case, so this is not for motors specifically, but there are some cases where you want to do something with PWM that you can't do with a linear amplifier. One of those is actually dimming, which is, I mean, it would be silly to do with a linear amplifier, but dimming an LED. So an LED actually requires a certain voltage to turn on. So if you use PWM to drive an LED, you can dim it down and then brighten it up by changing the PWM duty cycle, which we'll talk about. And that's something you can't do with a linear amplifier because the linear amplifier cuts off turning on the diode at a certain point. So sometimes PWM is required. Usually it's either or. For motors, it's always either or. So, okay, PWM. So it's a technique used to deliver an effectively variable signal to a load, in this case a motor, without a truly variable power source. A pulse of full source amplitude is repeated at a high frequency. So imagine that your source is 20 volts. The source that we're using in this lab is a 20 volt source. So say you wanted to put in 10 volts. How would you do it? So this is how you would do it. You would pulse the full 20 volt source amplitude at a really high frequency of 20 kilohertz, delivering a signal that is effectively averaged by the load dynamics such that its effects on the load are nearly continuous. The fraction of the period, t, that the signal is high or on is called the duty cycle, delta. Figure 8.2 shows a PWM signal V and its average, the V bar, with a few parameter definitions. So let's look at that. Figures down here, annoyingly. So we've got time, we've got voltage. So this was like our 20 volts, say. And if we pulse this at a very high frequency, then what we're saying is effectively you get the average of this signal that's felt by the system. Now, you probably learned a little bit about, for the frequency domain in your measurements class, but if you have not, it's not a big deal. We're going to talk about it extensively in the System Dynamics and Controls course next semester. The idea is that you can filter out different frequencies depending on your system dynamics. For most motors, really, really high frequencies effectively get filtered out. It becomes a low-pass filter. So a low-pass filter is going to allow through low frequencies and filter out high frequencies. Most of this stuff that goes into the square wave is high frequency. The average of the signal is low frequency. So you kind of get the average coming out when you go through a low-pass filter. And this 20 volts, I drew this to look more like, I don't know, 75% duty cycle. But say you pulsed it for half of the time on, you would get an average of 10 volts out. So I said we wanted 10 volts out. We could do a 50% duty cycle and get 10 volts out. So if W is the length of time that the voltage is on, and T is the period, big T is the period, then the duty cycle, delta, is just W over T, the fraction of the period that the signal is on. So the mean of any periodic signal with period T can be computed with the integral over a period divided by that period. So that's just in general how you average any signal, which is easily evaluated for the PWM signal. We just need to figure out what the area under the curve is, and the curve is a rectangle, so it's just base times height, and then we divide that by T. W over T is just delta, so the average signal is just A times delta. So if you wanted a signal that was 50% of A, you would do a 50% duty cycle. You'd have it on for half of the period. If you wanted one that was 10% of A, you would use a duty cycle of 10%, and the signal would be on for 10% of the period. And you would get an average signal back of 10% of A. So this result shows that if a PWM signal is delivered to a load, such as a DC motor, that is relatively unaffected by high frequency signals, the effective signal will be simply the product of the source amplitude A and the duty cycle delta. The duty cycle can have values from 0 to 1, so the effective DC signal produced varies linearly with delta from 0 to A. So it's really convenient if we can create such a signal. So it turns out that it's easy to do so with our modern electronics. So a microcontroller such as the Myrio or an Arduino can easily produce a PWM signal. It's actually in every microcontroller board I've ever seen, you've been able to create a PWM signal. It's pretty universal. However, this signal is typically low power and cannot drive even small DC motors. So even if you've got those little like toy DC motors, the Arduino or the Myrio doesn't put out enough power to supply to actually drive those motors. Therefore, it is common to include a special kind of integrated circuit that uses the microcontroller's low power PWM signal to gate a high power DC source signal for delivery to the motor. We use a connectorized printed circuit board, PCB, for example, a PC motherboard, the Pololu motor driver carrier, which if you go here, this brings up their product page for this. Pololu puts out a lot of nice motor driver carriers. And then here's the manual, and I recommend you go to these two sites. It includes on it, so on the printed circuit board, there is a very specific integrated circuit, the VNH5019, which is an H-bridge motor driver integrated circuit. So check those out. They're not super long, just pretty short manuals. And so just, a moment, let's step back and look at this for a moment. These Pololu products, they're really nice. They're really nice for doing any sort of prototyping. So you guys are, working in a lab where, you're going to prototype things with off-the-shelf boards like these. And these tend to be called carriers because they usually have one specific integrated circuit. In this case, it's the motor driver, the H-bridge motor driver integrated circuit that it's carrying. So it's a little board. It has it's centered around a specific chip, specific integrated circuit, and it sort of allows you to use that chip. It might have a little bit of like auxiliary electronics on it as well for like protection of that chip. And what it does is it allows you to put connectors on it, connect it up, and use that integrated circuit in your design without having to put it on your own motherboard, without having to design your own printed circuit board. So in a final product, a lot of times you would actually put this VNH5019 directly onto the printed circuit board yourself, and that would be the way it gets integrated into your product. It wouldn't go through this circuit board and then onto the other circuit board. Although you can do that, it's good to do that when you're doing any prototyping. But in the final product, typically you'd want to have it on one circuit board if possible. So usually that's what you'd want to do. Okay, so let's talk about H-bridge circuit. So this VNH5019 is an H-bridge circuit. So let's talk about these for a minute. So we want to drive DC motors at different effective voltages and different directions. So PWM got us different voltages or different driving signals, but different directions is going to be provided by the H-bridge. So the H-bridge circuit allows us to reverse the direction of the PWM signal delivered to the motor. So our supply, we could have a supply that can do positive and negative voltage, and then use PWM to gate that. But typically, we only have supply. I mean, they're more expensive, but you can get supplies that are differential, plus and minus. But we'd prefer to be able to use just a single-sided supply. So an H-bridge allows us to reverse the direction of the PWM signal delivered to the motor. So figure 8.3 is a diagram of the H-bridge circuit. So let's look at this. So this is just the first one. A is just kind of showing you the setup here. We've got a voltage source, we've got ground. We're going to apply that voltage across this motor, and it could be PWM, it could be something else, maybe just a variable linear amplifier. And we're going to apply that voltage to the motor, and we've got these 4 switches, and we've got these 4 diodes. So this is the H. You can sort of see the outline of the H here. So the H is in play, and now we're going to see how it operates. So there are 2 main driving modes. So the switches have multiple modes that I'm not going to talk about all of them, but in sort of main operation, you can drive it one direction if you have switch 1 and switch 4 on, and switches 2 and 3 off. So if that is the case, we have a circuit that connects S1 to the side of the motor, and then through S4 to ground, and we drive the motor in one direction. And in the other configuration that we'll look at, S2 and S3 are closed, and S1 and S4 are open. And in this case, we have voltage dropping across the motor in the other direction. So we have a nice reversed voltage in this case. So it drives the motor in the other direction. Current flows the other way. We get torque going the opposite direction. So this is great. This is what we want. And that's the main idea of the H-bridge. There are a lot of subtleties that come into play as well. And let's talk about one of them here for just a minute. So recall that the electronics side of a DC motor can be modeled as a resistor and inductor in series with an electromechanical transformer. The inductance of the windings make it an inductive load. You're going to hear that term a lot, inductive load, which presents the following challenge. We can't rapidly change the current flow through an inductor without a huge spike in voltage. And the switching power supply and the switching of the well, especially in this case, we're thinking about the switches of the H-bridge, do just that, leading to switch damage. So think about the inductor elemental equation for just a moment. So we have dIL dt equals 1 over L VL. If you flip a switch on or off, but especially off, in this case we're thinking of off especially, and your current was flowing, and then suddenly you turn it off, so you opened up a switch, so there's nowhere for the charge to flow anymore. It'll essentially be a very, very short transition from current flowing to current not flowing. The slope of this line is essentially vertical or infinite, negative infinity in this case. And that means there's going to be a huge voltage that's going to be created, right? So the derivative of the current is the voltage across the inductor. So a huge voltage spike will occur. And that's bad news for an inductive load. So we can't rapidly change the current through the inductor without a huge spike in voltage. Switches do just that, leading to switch damage. Therefore, during the low or off duration of the PWM signal, S1 through 4 cannot all be simply opened. Okay, we can't just simply open them all up because we're going to have this huge inductive load that's going to kick back. It's called. So there are actually a few options for switch positions that allow the current to continue to flow without inductive kickback. And so there are other configurations of S1 through 4. I'm not going to get into the details, but that's also an aspect that's used. So what's up with the diodes? Because we'll have 4 diodes too. So technically, they could be used to deal with the kickback. They can be used to continue to flow current even when you open up a switch. But since the diodes dissipate power, that's not really what we want in this case. It's not ideal. And the proper switching is the primary kickback mitigation technique. So we're gonna do some exotic switching in order to deal with this kickback. However, the diodes ease the transition between switch flips, which are never quite simultaneous. So say you did one of these configurations to flow power back and not have it damage your switches. The transition's never perfect, and so in the meantime, even if that's a very, very short period of time, the diodes sort of help mitigate that a little bit without causing damage. So that's what the diodes are in there for the H-bridge circuit. Okay, and H-bridges are actually, it's a lot of detail that you can go into, but that's the main idea. So there's a lot in this lab, and I hope that you don't get too overwhelmed. I hope you can get something out of these ideas. That's why I'm trying to stay pretty high level here. So voltage dividing. So this is another little aspect of this lab. So the myRIOS C connector has analog differential inputs that accept voltages in the interval from negative to positive 10 volts. However, the DC power supply used can deliver more than, but we will keep it to 20 volts, which is the maximum we expect to measure at the motor via pin Vout. So assuming that we don't have anybody messing with the flywheels, we shouldn't see voltages that are higher than the input voltage to these motors. So the voltage across the motor shouldn't be more than about 20 volts. It's a common situation, which is to say we can't measure up to 20 volts because we saturate at 10. So what do? It's a common situation that the analog inputs will not contain the voltage range that we would like to measure. The easiest method to mitigate this challenge is to use a simple voltage divider with known resistances R1 and R2, like we do in this figure here. We do not want to saturate the myRIO input, nor do we want the input to be so small that we lose resolution. So those are the two sort of design factors. So we want to divide the voltage down. We don't want to divide it down so much that it becomes tiny. It becomes tiny. Remember, we have this, analog input, but it has it's a computer at the end of the day, so it has to become digital. So you only have so much resolution. So you have, effectively, in this case, we really only have 0 to 10 volts. And you can only measure certain values in between, right? Some intervals. Maybe it's like 10 millivolts or something. So we want to take that 20 volts, it's up here, and we want to bring it down into this range. The 20 is the max, right? We don't want to put 20 down. We could put 20 down here, divide it way down. But then our resolution isn't very good. We only have a few voltage levels we can measure. So this is why we want to divide it down to just be right under our saturation, our max, and then but not too much below that, so that we have a lot of so-called dynamic range here. So we're going to use, in this case, we need about a factor of 2. We're going to just use 2 resistors that are about the same voltage. So 2 nominally 330K resistors will work just fine, dividing the signal in 2. You could use other resistors. I would recommend using high resistance resistors because you don't want to short out your signal here. So I mean, the higher the resistance, the better, essentially, because you want it to not to affect your system. So those resistors are pretty good. All right, so you want to load your voltage essentially. Great. So we can use that to divide the signal in 2. Oh, and also it's a little bit weird, but due to the way that the software that we're going to use that I wrote was written, I used R1 as the resistor name that we measure the voltage across. So R1 is here and R2 is there. So the V out comes from the motor driver, which has a pin that tells you what the voltage is across the motor driver. And we divide it by, in this voltage divider, and we get out the voltage across R1, and these go into our myRIO. So that's the setup it has. I really wish I had written it the other way, R1 and then R2, but you know, past me was just not cool. So now I'm totally cool, so that's fine. Okay, H5, measuring motor speed. Now, there's a lot, but we're getting there. Okay, so motor position and angular velocity are best measured by rotational quadrature encoders. Rotational encoders are made from a wheel with alternating dark and light stripes. The encoder we have affixed to the rear shaft is this HP model number with this manual that I have on the website. So it has black stripes on clear plastic. Okay, and you can actually see that there's one around. I don't know if you'll be able to find it, but there's one around that has the wheel actually visible, and you can see the very, very light lines. It's like, I think there's 400 or 800 lines on the wheel going around. So it's pretty cool. Great. A light source either reflects differently off the black stripes, or as in our case, passes the light through the clear plastic wheel into a photodiode, or is blocked by the black stripes. So the black stripes are going to block the light, and then the clear plastic is going to let the light go through. And so each time a stripe passes by, the photodiode detects a blink, okay, which is passed on to the myRIO via digital channels of the myRIO configured for detecting encoder outputs. So the encoder pinout is shown in figure A5 from the manual. So this is this guy here. And this is all connected for you, so you shouldn't have to worry about the connection. But it's good to know for the future how the pinout works for this and how you might consider connecting it up. So the myRIO with the LabVIEW software is all set up to read an encoder for you, so you don't have to do a lot of interpretation. Many of these microcontrollers are set up to read encoders so that you don't have to do a lot of writing of the code yourself to read the encoder, but there's always a little bit you have to do. Okay, so that's cool. You get the blinking, and you know it turned, and you know how many lines there are in 360 degrees, so you know how many degrees it turned when it blinked. Great. The only issue remaining is that a given blink doesn't give one piece of information, which is which direction the encoder is rotating. So say it went from dark to light, and then it went back to dark. You don't know if it continued in the same direction that it was going, or if it went back. So you don't know the direction of each blink. However, a clever technique called quadrature encoding can be used to determine the direction of each of these blinks. The idea is that if we double the number of stripes but offset the second set by half of a stripe width, then measure both channels, we'll call them A and B, then the direction can be determined by which channel leads the other. For instance, if we look at this figure, let's say that when we see high signal, that's when we see light at the photodiode. When we see a low signal, that's when we see dark. So light, dark, on, off. Okay. So if the quadrature encoder is set up so that the lines of A and B are 90 degrees out of phase, like this is, so half of a stripe width out of phase, and we see that in time, as we're going in time here, in time, if you see that B goes light and then A goes light, and then B goes dark and then A goes dark, if you keep seeing that pattern, you're continuing along in one direction. Let's say I arbitrarily assign it to be clockwise. Okay, so we know that if B leads A in being light, then we have a clockwise rotation. But then if A leads B, so if A turns light before B turns light, then we know it's rotating the other direction, and so this case we say counterclockwise, which, as long as the first one was clockwise, the second one would be counterclockwise. The idea is that they're opposite of each other. So that's how we can deduce which direction it goes. And you can think about it like this if you wanted to, which would be sort of a finite state machine way of thinking. If A is light and B is light, so that would mean you're in this band here. So A is light and B is light would be this region. Then the question is, if the next thing that happens is that A goes dark. If A goes dark next, then that means you're moving counterclockwise. But if B goes dark next, that means that you actually started going back the other way, right? Because B would have to go dark first if you moved left. If you moved right, A would have to go dark first. So that's how you can deduce the direction from any state to the next. It's kind of fun. Okay, quadrature encoders, tons of fun. It's good to understand them. It's good to use them. So measuring motor speed. We already talked about this. Quadrature encoders, blinking, great. Cool. So, step response measurements. Sorry, it's 2 a.m. I'm just sipping my fine Canadian whiskey. It's actually not that good. I really need to get something better than this. Like some rye, like a good rye. Okay. Step response measurements. In this lab, a step voltage input will be supplied to the motor until the flywheel has reached steady state speed. So say it's stationary, and then you put in a voltage suddenly. So think about the voltage. Say voltage is 0, and then suddenly you step the voltage up to some new voltage. We're going to do like 4 volts. 8 volts. And then the motor's speed is going to respond to some new velocity, okay? And then it'll reach its own steady state eventually, and then we're going to turn that back off. I'm just going to write right through my text here. Then we're going to turn that voltage off back to 0, and then the speed will decay to 0. And then we're going to keep doing that again and again, get an average. That's our idea here. So that we did this with a thermal response, right? Step input in the heating element, and then we let it decay back. This time, we're going to do it a bunch of times. We're going to step it up, and then we're going to drop it back down. We're going to step it up, drop it back down, and we're going to average those responses because we have gotten even more badass in the last couple weeks. So, great. With a single continuous measurement in time, the step input and free response will be repeated several times, such that the step responses can be averaged in post-processing. So we're going to just take a bunch in series, and then we're going to, in post-processing, move them around so that we average them in time. So, great. These step responses characterize both transient and steady state for the system. The mechatronics lecture course shows how such data can be used to estimate, as we will here, both the dominant time constant, tau1, and the motor constant, or transformer ratio, TF, with estimates tau1 and TF tilde. Tau1 tilde and TF tilde. It should be a bigger tilde. So this is what we're going for, especially this motor constant or transformer ratio, TF. That's what we want to estimate. So we're going to measure this for each motor. And each motor in the lab is going to have a little bit of a different one, although it should be pretty close to the one given in the manual for the motor. So we'll talk about this whole lab is actually going to be talked about in class quite a bit in the coming days. Okay, measurement setup. So check to make sure the PC, MyRIO, protoboard, motor driver, and motor are all properly connected before proceeding with the final measurement steps setup steps below. So get it all set up. Then make sure that you unplug the MyRIO power supply and motor power supply before you proceed with these next couple steps. So the motor power supply has a big yellow barrel plug on it, so it's plugged into the strip. Let's pull that out before you get going. The power supplies being disconnected is important for this because if you connect it improperly, I did the ones that are most dangerous, I guess, or they're not really that dangerous, but they could melt some wires if you do it incorrectly, and you could break something. So just try to be careful with it if you can. So I want you to do the connections and double check the connections and then plug stuff in. Okay? So that's the plan. So before you do that, measure and record the actual resistances of the two resistors you got. So say they were 330 ohm nominal. If there aren't 330 kilo ohm nominal resistors, then choose something close to that and then measure them and write the actual measured values down. Using a breadboard and these two resistors, build a voltage divider to divide the motor driver voltage across resistors R1 and R2, like we discussed before. And then use this figure that we just scrolled past to make the remaining connections of the motor driver carrier to the MyRIO C connector with the voltage measurement across R1. So this is the part where you guys come in and have to do some stuff. Okay, so this motor driver carrier is connected to the motor. It should already be connected to the motor, but make sure it is. This one, it doesn't really matter that much if it's red and black in this direction or black and red. It just means that one's positive. It turns the motor one way or the other way, positive and negative. It has to do with a sign, not a big deal. This power supply actually should be, make sure this is connected black and red. That one's actually important. It will probably fry the board if it's connected in the opposite way. So that would be bad. Okay. Good. I don't have any extras either, so your classmates will be mad at you. Okay, so this is the board, and on the other side, so you guys don't have to make any of these connections over here, but you should check them to make sure that they're there. On the other side, we've got, some of these are already be connected. I've already connected up for you, or they should be connected, VDD and ground. So these are essentially what are the power for the this circuit. The circuit itself is being powered through these. And I also have connected up these three. So I'll put a check, or I'll put a dot. Ground, VDD, I should have connected those already. And in B, in A, and PWM should all be connected for you, okay? If they're not, then connect them up to the corresponding locations on the proto board. So these are digital pins 8, 9, and 10. The proto board, let's scroll up and look at it. I think it's close enough to see it. The proto board has, you can't really see, but this says digital. These are the digital pins for connector A, all along this column here. So digital pins 8, 9, and 10 are, I think, here, here, and here. Oh, there. Okay, so that's where they should be connected to, and hopefully they are. And the power, the VDD and ground, they could be jumped off of here, which I think they are in this photo. They look like they jumped off of there. Or they could be jumped off of the other side of the board's got them as well. So I think that it's like here and here, powering the driver. So those should be the connections. The encoder is what this connector is, and that should be connected up there. Yeah, okay. Whoa, too zoomed in. Scroll way back down. Where were we? Aha. Okay. Good. So we've got those connections that they should already be there. So I want you guys to connect up now. It's a few. Okay. So you're gonna want this current sense pin and this ground. This ground, you're gonna want to go to. So I connect this up to one of the proto board ground pins. But there are several ground pins on the proto board. Grab another one of those proto board grounds and go into a breadboard. So go into your breadboard, and this, let's see, this will work. This stuff is going to happen on your breadboard. Really, it's just, well, I'll just stop it there. Really, it's just there. That's all going to happen on your breadboard. You're going to build this voltage divider here, and you're going to connect up this ground. You're going to want to actually, I'll move it back down. You're going to want to jump it off of the breadboard to get to your A ground on C channel. But yeah, so A ground is on the C channel as well, so C channel, A ground. You just need extra connections there. So great, 2 resistors in series. You're gonna put the voltage out from, not Siri, in series. V out is going to go across both resistors. We're going to drop it to ground pin, and then we're going to take that and we're going to go into the myRIO. We're going to measure just the resistance across, or the voltage across R1. Remember, because it's half of the voltage across both, half of V out, and that gives us a voltage we can handle that doesn't saturate. So that's the idea there. Okay, so you guys are just going to handle this one, current sense pin, this one, which is the ground, that ground, this one, which is the ground side of your voltage divider circuit, this one, which is the high side of your voltage divider circuit, so this one, and then you have to connect these up to the myRIO as well, the C connector. So make that connection and that connection, and then this connection. Okay, so those are the connections you guys need to make. Just take your time. There's not a lot you need to do in this lab, and the actual measurement just takes a few seconds. So take your time, be methodical, check that everything is correctly connected, and then plug it in. Okay, only then plug it in. Great. Yeah, so now plug in the myRIO power supply and the motor power supply. Okay, great. And then so if you do it in that order, then you don't have to worry about any potential electrocution, although it should be fine. The power is not on the side of the circuit you guys are going to be connecting to in the motor driver. The power is on the other side, which is the back side, and just don't go like poking around back there and you'll be fine. Okay, measurement procedure. So download the LabVIEW VI here. So this is zipped, so unzip it. Make sure you unzip it. I always say unzip it, and then somebody doesn't unzip it. So unzip it, and then open up the project file. Don't forget those steps. The project file, not the VI file. The project file. Once you're in LabVIEW, in the project file, then open the main VI file. Okay? That's the order to do it. Just like it was before, but I know sometimes it's hard to remember. Once the VI is open, navigate the front panel, navigate to the front panel and enter the measured values for the voltage divider resistances R1 and R2. Make sure you get them correct, which one's R1, which one's R2. Remember, R1 is the one that we're measuring the voltage across into connector C. Zero the duty cycle control slider and run the VI. So the VI has a duty cycle slider, so grab the slider and move it to 0 and then run the VI. So it should deploy and run, and if you increase the duty cycle from 1 to even like 0.05 or 0.1, then it'll start to rotate. Okay. So play around with the motor speed by sliding the duty cycle control, so you can move it back and forth. That's great. So here's the caution box. So there's a toggle switch. I should put a photo of the VI on here, but there's the slider, and there are actually two sliders, so I'll talk about that. There are two sliders. One of them tells you the duty cycle. It goes from 0 to 1. They're both duty cycles, 0 to 1. One of them is the control, so you can actually grab this upper one and slide it. The other one's the indicator. And the reason that I have a control and an indicator is that when we actually start to take data, I'm going to be automatically changing the duty cycle, and the indicator will show you what the actual duty cycle is that's changing. Otherwise, the bottom one should follow the top one as you grab it around manually. Okay, so slide it up, you start to see the motor turn one direction. There's also a big toggle switch up here. So it looks something like that. The switch, you toggle it down or up, or I don't know, whatever one it is in that direction. It'll switch the direction of the motor. So it'll do that effective, it'll switch your H bridge, okay? So you get to change the direction of the motor turning. Now, here's the caution. Before you toggle the switch, bring it down to 0 and then toggle the switch. If you have the duty cycle up here, like 0.6, and it's moving in one direction at a pretty good clip, then you flip the switch, it's going to then be putting that voltage across the other direction. And there's pretty good chance you're gonna break something if you do that. So I was gonna put in a programmatic control there, but I didn't have time to do it. So don't, just try to be cautious. I know that sometimes accidents happen. I'm not like, don't like be too afraid to touch anything. But just be cautious. Like you guys have some responsibility to I guess behave in a professional way. So we're in a professional school here, right? So this is an important case. You'd break things that cost hundreds of dollars. It's not like the end of the world, but it's just, nobody likes to have to go ask their dean for money all the time because stuff breaks. So at least I'm trying to warn you guys not to do that. But if you do it, at the end of the world, please do let somebody know if you do break something, so that it tends to be a bigger safety hazard if something's broken. So, okay, great. That's the toggle switch caution. All right, so after everyone has had a chance to change the motor speed, set the duty cycle, this is pretty fun. So have fun with it. Move the duty cycle up and down. You're not gonna hurt it by moving it up and down at all. Just make sure that it's down when you switch the direction. Great. Use the execute button to run at least 6 cycles with a default parameter. So what the execute buttons are going to do is it's going to step up the voltage. So say that you're stopped to start, stopped at the beginning, and you set the voltage up. Oh, look at this angry face. You set the voltage up, and that's what the execute button will do. It'll set it up to 40% duty cycle. And then it'll do that for a certain amount of time, and then it'll shut off for a certain amount of time, and then it'll go back up to 40%. And it'll just keep doing that for forever, actually. So it'll keep doing that, and your motor is going to speed up. Hopefully you get to a steady speed, and then slow down, hopefully to a steady speed, and then it's going to speed up. So that's the repetition that's going to happen. It's going to be averaging these, and then it's going to slow down. So a couple things to note. So the motor should speed up to a steady speed, then slow to a stop each cycle. We don't really want it to stop for a long time, so just stopping is about right. If the motor does not slow to complete stop in each cycle, consider increasing the interval divisor and running it again. So there are some options at the top that allow you to change the division, the number of samples for each interval here. And if you increase the divisor, it goes longer. So that's why I say increase it. The default parameters I put in there as 40% duty cycle, which is fine. You can go higher or lower if you want, but I think that 40% is a pretty good place to be. And then so I think that the divisor, you can feel free to do it, mess with that a little bit if you want, but also shouldn't need a lot of tweaking. Great, so press the stop button to save your data. So let it go for about 6 cycle. So I mean, it might take a second or two, a few seconds per cycle. So you don't really need to let this thing run forever. And in fact, I would encourage you to not let it run too long. Otherwise, you're going to get a ton of data, and it might start to lag if the RAM starts filling up. So 6 cycles is good. 20 cycles is fine. 2,000 cycles would be definitely too much. So you're going to watch this thing speed up and slow down, speed up and slow down. Get a nice run in so that you get some good data, and then hit stop button to save the data. Report requirements. So then you do the usual thing, copy the data file over, but then make sure that you open it up in MATLAB using the same techniques that we've learned before. So it's the same sort of data file. So open it up. Before you leave the lab, make sure that you have good data in there before you get going. Report requirements. Oh, I changed, but now I just look dumb. Okay, write a detailed report of your experimental results as outlined in the report template. Pay special attention to the following. 1. Estimate the non-zero steady state value of the angular velocity omega j infinity, include a 95% confidence interval. So I'm going to talk more about these in class. So I'm actually not even going to read through them because they're not going to make a ton of sense right now. But in class, we'll talk more about how to do each of these steps, which can be a little tricky. In the class, what we'll do is we'll spoof some data, and then we'll do this analysis. So I want you guys to follow that procedure with your data, and you'll get an estimate for TF, and you'll get some nice curves and some nice confidence intervals. So the confidence interval discussion is mostly coming from your measurements class. So least squares, regression, linear fit, all that, and then confidence interval. Those are concepts from measurement. So I encourage you to review those. The main thing that I think that you guys need to look at is how to do a linear fit. You guys already did that in this class once, so I think you'll be fine. And then the least square, and then where is that? Well, somewhere I say, oh, standard deviation. Yeah, you want the error bars to be 1 standard deviation of the means for each point. So it has to be a standard deviation of the means because each point is going to be a mean. So let me sort of show you a little bit of what that is like. So we've got our motor speed response, and actually they're not necessarily the same time constant, so I should try to exaggerate that. So this one's like relatively short, say, and this is the long time. It didn't look long at all. The long time constant. So you've got multiple of those. What we're going to do with the data is pretty much this. Well, one of the things we're going to do with the data is pretty much this. We're going to take each interval, and it would be nice if it had just matched, but it didn't. But we're going to make it match. Except for not. We're gonna essentially take it and not do the scaling because it'll be scaled correctly. But we're gonna take this thing that was here, okay, so it was in series. We're gonna take it and we're gonna average it with each of these previous attempts. We're gonna average each point down here to the, oh, hey, I'm back. Looking a little haggard though. Each point here we're gonna average. So if this was, say, like 6.2 volts, and this was 6.0 volts, then the average would be 6.1 volts. Okay, and then you're gonna at the end have one plot that looks like this, and then like this. That's your average plot. So each point has an average. Now, these points should match up actually because you constructed it yourself. So the points should match up. You should get a nice curve here, and what you want then is for this point, this is your average. So say you only had 2 runs, 2 cycles, but you want to have more than that in reality. So this would be 6.1 volts. It's a mean. What you want to plot an error bar of then is the standard deviation, plus or minus 1 standard deviation of the mean. This is a term, standard deviation of the mean. That's what you want to plot for each of these points. Okay. I don't want to get too much. I don't want to keep going too much because it's already been a long intro lecture. But fortunately, the actual lab exercise isn't too long. You guys don't have to write the LabVIEW VI yourselves. So go ahead and get started. And yeah, I think that you'll be good to go. Let me know if there are any questions. We're going to talk more in class about this too. So let me know in class if you have any questions on the lab as well. All right, good luck.